morning friends, I welcome you all in this session. As you are aware, in previous session we discussed continuous probability distribution, and the distribution which we discussed was normal probability distribution. As I have said, one of the widely used distributions, and we have calculated probabilities in upper tail, in lower tail, and we have also calculated probability between any 2 points under the curve. Let us look at one more example, it is quite a simple one. So, a supervisor whose name is Dennis Hogan is working at hydroelectric dam. So, he knows that the dam's turbines generate electricity at the peak rate when at least 1,000,000 gallons of water pass through the dam each day. Otherwise, the electricity would not be generated at its peak rate. He also knows from his experience that the daily flow of water is normally distributed with a mean equal to the previous day's flow. So, from experience he knows that the mean would be the one it would be equal to whatever water was flown in yesterday, right. Now, a standard deviation of 200,000 gallons, and yesterday 850,000 gallons flowed through the dam. Now, what is the probability that the turbines will generate at its peak rate today? So, what information you have been given? It is mu, right. What is mu? It is mean of yesterday's flow, right. So, this 850, is not it? What about standard deviation? It is 200,000, right. And what is x value over here? It is just 1,000,000, right. So, x is equal to 1000, right, or 1,000,000, right. Now, let us look at, first of all you should convert this x value into z value, right. So, probability that the electricity would be generated can be calculated like this. So, this is x minus mu divided by sigma. So, z value is equal to 0.75. Now, look at this table and what is the area when z value is 0.75. So, 0.7, this is 0.7 and 5 is, so this is 4 and this 4 and 5. So, this 0.27, so let me redo it. So, this is 0.2734, this value. Now, so we know that this area is 0.2734 and we also know that this entire area is 50% or 0.5. So, what we are interested in? We are interested in finding this area, right, this area. And how we can find it? Since we know this area, we know the entire area. So, we will subtract 0.2734 from 0.5. So, we will get answer as 0.2266, right. Now, let us move on to the approximation of binomial distribution. We have seen earlier that we can use Poisson distribution instead of binomial distribution, and both of them are discrete distributions, but Poisson distribution can also be used instead of normal distribution. So, let us look at, in fact, normal distribution can also be used for binomial distribution. It is not the Poisson distribution for binomial distribution, it is the normal distribution for binomial distribution. So, when the number of trials n becomes large, evaluating binomial probabilities are quite tedious. So, there is a solution to this particular problem. So, normal probability distribution provides an easy use to approximate binomial probabilities. So, if NP and NQ both are greater than or equal to 5, we can use normal distribution instead of binomial distribution. So, just remember these two conditions. And what were the conditions when we used Poisson distribution for binomial distribution? The n was equal to or greater than 20 and p was less than or equal to 0.05, right. So, these are two different conditions for approximation of binomial to normal, right. Now, this is the mean, we know that it is mean of binomial distribution NP and NPQ, right. So, this is standard deviation is under root of our variance is NPQ, right. So, variance you can write like this NPQ, right, is not it. Now, since this is a case wherein normal distribution is continuous and binomial is discrete. So, there is a need to add and subtract 0.5, which is also known as continuous correction factor, because we are using continuous distribution to approximate discrete distribution. So, for example, if p x is equal to 10, so rather than going for probabilities of p x is equal to 10, we will subtract and add 0.5 from 10. So, it would be 9.5 to 10.5, right. So, we will calculate probability in this, right. So, x has to be less than or equal to 10.5, but more than or equal to 9.5, right. So, this is something which you need to remember, continuous correction factor. Okay. Now, whenever you get some data either from primary source or from secondary source, you should check it for normality, because this is one of the assumptions to carry out several statistical analysis. For example, if you are going for let us say regression, then some assumptions are to be fulfilled, and one of them is that the data should be normal. Since we are discussing normal probability distribution, so you should know how to find out whether data are normal or not. So, we should evaluate normality of the data set, right. So, first of all, you should remember that there are several continuous distributions, but all of them are not normal. So, to have normal distribution, certain conditions are to be fulfilled by the data set. So, it is important to evaluate how well the data set is approximated by normal distribution. Normally distributed data should approximate the theoretical normal distribution. So, whatever is normally distributed data, they should fit some theoretical distribution, some theoretical points. We all know that normal distribution is a bell shaped curve, it is a symmetric curve where mean, mode and median are equal, right. And we also know that the empirical rule applies to normal probability distribution. So, empirical rule is what? It is within 1 sigma limit you have got approximately 60% of data points, within 2 sigma limits 95, and within 3 sigma limits it is approximately 99.72, right. And one of the other characteristics of normal distribution would be IQR should be 1.33 of standard deviation. So, whatever is IQR, interquartile range, this should be equal to 1.33 of standard deviation of data. Then you may say that the data are normally distributed. So, these are some of the conditions, and there are many more conditions. So, let us look at data characteristics to theoretical properties. So, first of all, to ensure or to check whether data are normally distributed or not, you should construct a graph or a chart. So, if data size is small or it is moderate, then it is always good to construct stem and leaf diagram or box plot to check the symmetry, right. And we know that what is stem and leaf diagram, and we also know box plot, right. In box plot it looks like this, is not it? This is what we have discussed earlier. So, if this point is, and this is known as median, right. So, this q1 q3, right, q1 q3 and this is median value, right. So, if this median value is in between here, then we will say the distribution is normal, right, or it is not skewed. So, if data set is quite large, then rather than going for stem and leaf diagram and box plot, it is always suggested to go for histogram or polygon. So, that will give you an idea whether histogram is taking bell shaped curve or not. So, these are very visual ways of identifying whether data are normally distributed or not. But a better solution would be to compute descriptive statistics of the data set. So, if you get mean mode median equal, then of course, it would be a normally distributed data. If IQR is equal to 1.33 standard deviation, it would be normal data. If range is equal to 6 standard deviation, range is difference between maximum to minimum. So, this will also give you an idea about normality of data. Now, after looking at descriptive statistics and graphs and charts, you should observe the distribution of data set. So, if you think that approximately 2/3 of observations, or it is approximately 66.66 or 66.67% of observations lie within one standard deviation, we will say it is a normal data. Otherwise, 80% of observations if lie within, let us say 1.28 standard deviation, then it would be again normal data. Approximately 95% of the data lie within 2 standard deviation. So, if you fulfill all these 3 conditions, you can say that data are normally distributed. Now, apart from these methods, there is something called normal probability plot. So, if you draw a normal probability plot, we will see how to draw a normal probability plot, and if it is linear, then we will say it is a normally distributed set of data. So, for normal probability plot, arrange data into array, right, find corresponding z values. So, you have got let us say x1, x2 and so on, right, let us say x10, right. So, corresponding to these x1 and x10, you can easily calculate z1 and z10. So, how would you do that? Because you can easily calculate mean, right, and standard deviation, is not it. So, how would you calculate z1 for x1? So, it would be let us say z1 is equal to its x minus mu, right. So, x1 is let us say 10, right, 10, and let us say mean is 15 and standard deviation is 3. So, this is how you can calculate z1 and z10. Okay. So, plot the pair of points observed. So, in other words, let me put it in this way. So, plot x values on vertical axis and z values on horizontal axis. So, if you see a straight line, then it would be a normally distributed data set. So, if it is we evaluate the plot for evidence of linearity. If it is straight line, then it would be straight line means a line like this, right, having 45° angle from x axis, right. So, let us look at, so this is an example, a normal probability plot for data from normal distribution will approximately be linear. So, just see this is quite a linear one, is not it. So, for x is equal to 30, z is minus 2, and for some other value of x, let us say this, let us say this 60 or 70, right, z is plus 2. So, you can draw x and y, x and z values on vertical axis and horizontal axis. So, these plots will give you an idea how data are skewed, whether left skewed or right skewed. So, a plot like this is nothing but left skewed data, right, and a plot like this is right skewed data, right, and this is a kind of rectangular plot. But how normally distributed plot would look like? If data are normally distributed, it would look like this, isn't it? A linear line. Okay. So, if you have got a data set, then you can evaluate again for normality. So, first of all, you just come up with descriptive statistics. So, this is nothing but 5 number summary. So, you can calculate mean, mode, median, standard deviation, then variance, then IQR and so on, right. So, this is a box plot. Now, this one is skewed to the right. So, this skewed to the right means this is this kind of distribution. Okay. So, we will see whether the data set from which we have found out this descriptive statistics was normal or not, right. So, let us look at this. So, you have calculated all these descriptive statistics. So, mean was 21.84, median, mode, minimum value, maximum value, range is this, right, variance is this, under root of this variance is standard deviation, skewness, kurtosis. There were 318 data points and standard error is 0.36, right. So, we will see whether the data set from which we obtained this descriptive statistics was normal or not, right. So, if you look at this, the mean is 21.84, median 21.65 and 21.7. So, all are almost equal, right, and we know that in a normal distribution all these are equal, right. So, this first point, right. IQR is approximately 1.09. What is IQR here? IQR is not given here. So, you need to calculate. IQR is what? It is Q3 minus Q1, is not it? So, Q3 is 24.74 minus Q1 is first quarter is 17.76, right. So, if you subtract 17.76 from 24.76, you will get IQR, right. So, IQR would be 6.9 or approximately 7, right. So, if IQR is 1.33 of standard deviation, we will say that it is a normal distribution. So, it is not exactly 1.33 standard deviation, but it is 1.09 standard deviation. So, standard deviation is what? It is 1.42, right. So, it is 6.42, right, 6.42 into 1.09. So, you will get IQR as 6.92. Okay. Range is equal to, and we also know that the range has to be equal to 6 standard deviation, is it? So, it is not exactly, the range is equal to 9.26 standard deviation, not 6 standard deviation in this particular data set. Let us look at the other criteria. So, if we have 68.26% of data points within one sigma limit, we will say that is normal, but here in this case it is not 68, but it is 77.04%. Again 80% of data should be between 1.28 standard deviation. That is what we have seen in one of the slides earlier, is not it? This is what we have seen, 80% of data within 1.28 standard deviation, is not it? Is it there in our example? No, it is not 80%, but it is 86, approximately 87%, right. So far as within 2 sigma limits or within 2 standard deviation, you should have 95.44% of data, but here it is 96.86% of data points, and skewness is 1.69, kurtosis is this. So, in normal distribution, each of these statistics equal to 0. In fact, we will look at this particular part a little later. So, for the time being, you just do not look at this, right. So, skewness in this particular case is 1.69, yeah, this is skewness, and kurtosis is 8.46, because we will look at what should be the values of skewness and kurtosis for normality. We will look at in some other session, right. For the time being, don't consider this point. Okay. Now, we will move on to the third continuous distribution, which is exponential probability distribution. So, we have seen already two continuous probability distribution. First one was uniform and the second one was normal. So, this is another continuous distribution. It is closely related to Poisson distribution. What we have seen in Poisson distribution? In Poisson distribution, we calculated probability of happening of an event within given interval of time, but here it is just converse to that. Here what we try to do? We try to find out probability distribution of the times between random occurrences. So, it has got close relationship with Poisson distribution, and we can describe the exponential distribution with several characteristics. So, first of all, exponential distribution is a family of curves. So, the shape of the curve would depend on lambda, or is the mean, right, mean arrival rate. It is skewed to right, it is always skewed to right, it is never skewed to left. The x value range from 0 to infinity, and the apex value or the peak value is always at x is equal to 0 of the peak value of the curve. The curve steadily decreases as x gets larger. So, we will see all these points in next slide. So, let us look at this graph of exponential distribution. So, as I said, it is a family of curves. So, these are different curves. The peak value of this curve is here, and this peak value is when x is equal to 0. This is what we have said in previous class, right, in previous slide. So, apex, its apex is always at x is equal to 0, right. So, when you increase x from 0 to some positive value, then you can see that these lambda values decreases, right. So, this is exponential distribution for lambda is equal to 2, and this one is for lambda is equal to 0.2, right. So, an exponential distribution can be characterized by one parameter, that is lambda, right. Each unique value determines a different exponential distribution. This is what we have seen here. resulting in a family of exponential distribution. Exponential probability distribution is useful in describing time it takes to complete a task. What we have seen in Poisson distribution was the probability of happening something in a time interval, but here what we would calculate what is the how much time a task takes to complete it. So, the exponential random variable can be used to describe exponential distribution. So, let us look at some of the examples of or applications of exponential probability distribution. The exponential random variable can be used to describe these processes. Let us say time between vehicles arriving at a toll booth, is not it? Time required to complete a questionnaire or distance between major defects in a highway, right. So, these are couple of applications wherein you can use exponential probability distribution. The exponential probability density function, if fx is equal to 1 upon mu e to the power minus x to the power x by mu for all x greater than or equal to 0 and mu equal to greater than 0. So, here mu is mean, right, and e is equal to 2.71. We will work out an example. So, this is how you can calculate cumulative probabilities for some specific x 0 is some specific value of x, right. So, this 1, so 1 minus e to the power this. Okay. So, let us look at an example, Al fuel service pump. So, the time between arrivals of cars at a petrol pump or gas pump follows an exponential probability distribution with mean of 3 arrivals per minute. So, number of vehicles coming at a gas station or a fuel station is 3 per minute. Now, we would like to know the probability that the time between two successive arrivals will be 2 minutes or less than 2 minutes. Okay. So, let us look at this. So, the probability that the arrival would be 2 minutes or less than 2 minutes, right, equal to or less than 2 minutes would be e 1 minus e to the power x by mu, right, here mu is 3. So, this is your answer 0.4866. So, one of the properties of exponential probability distribution is that the mean and standard deviations are equal. So, in this particular case the mean and standard deviation would be 3 and of course, variance would be 9. We know that the exponential distribution is skewed to right, we have already seen this, and skewness measure of exponential distribution is 2. So, with this let me summarize what we did in today's session. We have seen a couple of examples on normal probability distribution. We have also seen how to evaluate normality of data set. So, there are certain parameters on which you should check your data set for normality. The example which we have seen in which most of the criteria were not fulfilling. So, we would say that our data set was not normally distributed, and we have also seen exponential probability distribution wherein we want to find out the distribution of probabilities of times rather than the probability of occurrence of an event within time intervals. So, thank you very much for this particular session. We will have a next chapter in next class. Thank you.